Good evening, everyone. This is Paul Ian Kabasag, and welcome to Math 273B. Thanks so much for coming here today, and I'll be presenting to you my presentation on optimization of manifolds. I really greatly love the lecture from our professor, and I would like to thank him for all the information that he's given me and assistance for this project. And and today we're going to be talking about the implementation of geodesic data analysis on manifolds. So to give you more of like an overview before I talk about each particular aspect, uh, what we're trying to do here is how can we perform the data analysis on nonlinear data sets? And that's going to be the underlying question that we'll answer throughout this presentation is how can we use geodesic data analysis in order to uncover the geodesic metrics on our manifolds. And mainly how it relates to data science is we're going to be using supervised learning and in order to perform a regression algorithm such that we can use past trained data and learn from the future labels and find the shape of the data allows us to predict on future data. And another way that we can apply geodesic data analysis is in unsupervised learning, where we do a clustering algorithm that can perform on past data without future labels. In this case, we need to find the underlying embedding of the or the probability distribution of the generated future data. So for this project, we'll only focus ourselves with geodesic regression and hyperbolic embedding models. There's a ton of packages out there in Python, which I will cover some, but mainly we'll only talk about Numpy and Geomstats and kind of show you how you implement geodesic data analysis. So without further ado, let's begin. So mainly, I'll start off with the math aspect of manifolds and geodesics, and then we'll implement the Python subsequently. So what is a mathematical definition of a manifold? Well, first of all, this is a topological space that resembles a Euclidean space. So as we've been exposed to in the past, Euclidean space, very commonly we know how to measure the distance of a line using Pythagorean theorem or distance formula. But when it comes to a general manifold, this doesn't really hold the same metric, and we have to involve what you call a geodesics, which I'll define in a bit, where this is the shortest distance between 2 points instead of the applying Pythagorean theorem, because it's not valid anymore because there's no particular metric called that's similar in manifolds. So to define what are the types of manifolds first, well, you can have a line, which is a 1D manifold. You can have a surface as a 2D manifold, or a sphere, a 3D manifold, or sometimes what we call a hyperbolic space. So that's what we're going to be focusing more on today. And for a manifold, like I said, it does resemble Euclidean space, but it's not the same. So since this is the case, we're going to need to perform some mappings. So that's going to be the main computation of how you use manifolds for data science is you're going to be doing some back and forth mapping between from space to space. So first of all, just to define what these are. So when you have this a surface for a sphere that's not homomorphic to the Euclidean plane, and you want to, because it has a global property that Euclidean space does not have, what you will have to do is to perform a chart mapping. Another example of a mapping is transition mapping, where you have two charts that don't overlap, but you want to transition them so that they can pass through one another. You can do a transition map. And one of the other features of a manifold that is that we want to embed and use is what you call the different types of manifolds that you can find. And first of all, what they are topological manifold. Apparently, this is what you call every manifold. So it's not really like a subcategory, but what to define what this is it's just a topological space, locally homomorphic to a Euclidean space, which means that every point has a neighborhood for which there exists a homomorphism mapping from that neighborhood to the Euclidean space. And this homomorphism or mapping is what you call a chart map, as I already mentioned. And the second type of manifold is what you call differential manifold. And you can add differential manifold into the topological manifold really easily. Mainly what this notion means is to add some differential calculus metrics into your manifold, where you can define the tangent to a point, and from that point, can you create find the velocity of the point as well as the acceleration, so on and so forth. And another type of manifold is giving it metrics to kind of like vectorial metrics, and what you use here is what we call a Riemannian manifold. And some of these metrics are pretty common in the Euclidean space, but let's just redefine them now for the manifold space. They're called lengths, areas, angles, volumes, curvatures, and divergence. Most, for a differential manifold, obviously you're trying to create a tangent to a point or to a vector. So in this case, you already have this tangent space, and so by this essence, you already have this Riemannian manifold. So it naturally applies. So that with all that preliminary background behind us, let's talk about how we can motivate using manifolds for data science. So in data science, we typically have two types of learning, machine learning, and this is what we call supervised learning and unsupervised learning. And in supervised learning, this is typically when you have classification or regression. For this project, I'll be talking about regression specifically. And when you do a regression, let me just talk about it here while I show you this. Is you want to be able to perform, given a data set, you want to be able to perform a regression by plotting a line or that kind of describes the underlying shape of your data. And in essence, when you do a linear regression, this is what you get, this straight line plot. And then when you have a nonlinear data, which is what we're typically have to encounter, or what you'll encounter in the field more, this linear data or linear regression really doesn't work as much and doesn't really capture the model as much, has a low performance. So you would have to focus and kind of move towards a nonlinear mapping. So when you do that, you're gonna have to use another type of distance. So just to step back a little bit, when you're served with a linear regression, a linear model, you have to use a linear distance, or as I said, the Pythagorean theorem. So this is going to be the distance between these 2 points, would be the straight line. You just apply the distance formula. But in essence, what about this green curve? How would you compute the shortest path between these points along this curvilinear line? For a nonlinear data set, this isn't so simple, but then we have a name for it. I also want to introduce it now. It's called a geodesic. So geodesics is the shortest line between 2 points along a curve or along a manifold. How we're gonna want to do this is we want to be able to compute this geodesics or metric in order to actually plot this curve manifold. And for supervised learning, this is mainly the workhorse, is to find the line that is the underlying structure of your data, so that you can predict new data. You can predict new labels from new data. So in order to do that, we will have to measure geodesic distances, and we will have to minimize these distances so that we actually have the shortest curve or distance between these lines, so that you can create this nonlinear curve. And hence, instead of using linear regression, we're going to be using geodesic regression, which I'll explain in a bit. So with supervised learning, as I mentioned, that's when you are given a training set data with past labels. And in these labels, we have to create this line using some type of regression, either linear or geodesic regression. and then feed it through the system, and then and now we use it on new data or future data in order to predict. But in unsupervised learning, we're going to have to use some other algorithm, and this is instead of a regression, but we're going to be using clustering algorithm. And the basic notion of unsupervised learning is not having any type of path label, but kind of learning from the data. And in our case for manifolds, we're going to be learning the embedding. And an embedding is just given this nonlinear data set or any type of data set, I want to be able to create this or find this geometric structure called a manifold that shows us the pattern of our data set. And then from this manifold, we can perform that analysis so that we can cluster and group and find different ways that these data points are similar within this manifold. Hence, we're going to be performing an embedding algorithm or embedding clustering algorithm. So just to talk about that more, so as I mentioned, when you're faced with a nonlinear type of data, you don't want to be using the straight line distance. You have to be using the geodesic distance, which allows you to perform a nonlinear distance computation of the shortest path between 2 points. And then when you perform a cluster, you have to find the central point. That's going to be the middle of all your clusters, groups. And you don't want to be using the linear mean in this case, because then it doesn't lie within your data. Even though it's in the middle, it really doesn't perform well because it's not within your data. But when you use shortest path distance or geodesic distance, you can compute this nonlinear mean of your data set, and is more accurate because it lies on your data. So to kind of bridge theory and practice, as I mentioned, we'll be using Riemannian manifolds so that we have this metric notion of a geodesics, which is the shortest distance between 2 points within a manifold or a curved space. In order to do this, we need to perform geodesic learning or geometrical learning, where we have to, in a Riemannian manifold, typically how this is done is you have to define a inner product between tangent vectors at each point. And to do this, we're going to have to perform mappings, as I mentioned. And then these types of mappings I'll talk about in a little bit, which are called exponential and logarithmic mapping. So now that we talked about the some background, let's actually move on to some of the mathematical constructs. So first of all, let's start out with this geodesics. So this geodesics, as I mentioned multiple times, is just a general concept of the straight line in Rn. To show you how it looks like, so if you're served with this type of geometry or manifold, and you want to find the shortest path between 2 points, this red line is what you call a geodesics. And then also, once you have this geodesics, it has some differential properties. So the same way where you can find first derivative and second derivative of a point, you can find first derivative and second derivative of a vector field. And for a geodesic curve, it has a velocity vector field, and along with it are these properties, as well as an acceleration vector field along with these properties. But the more important aspect here is defining what a tangent space is. So back in calculus, when we defined a tangent to a point, that's when you define what a differential is at a point. And in our case, a tangent space is a space spanned by our tangent vectors at a point in a manifold. It can be visualized as a tangent plane at a point in a sphere. So having a sphere, and at each point of the sphere, you have a plane that's tangent to that point in a sphere, and that is your tangent space for each point. And then just to repeat this multiple times, which I'll be talking about it more, and it's going to become clear, is there are no vectors in a Riemannian manifold. There's only vectors are only defined in a tangent space. So that's this tangent plane, tangent space that's defined at a tangent at a point, now in the manifold. Since this is the case, you're going to have to perform mapping in order to do some analysis. So you're going to have, for each point of on the manifold, you have to map them to the tangent space, perform some calculus. From the calculus, you put it back to the manifold to compute new points. So before we talk about that, let's talk about the generalization of of the derivative of a point on a manifold, and we call this the affine connection. An affine connection is this del on a manifold, is a mapping between del by of this affine connection that maps it back to the affine connection. So this vector fields with affine connections have these underlying properties. So you have linearity, R linearity. You also have this product rule, along with with any product rule for derivatives. This is the same exact thing. And as I mentioned, since this classical directional derivative defines an affine connection, and when you look at this equation, this looks like our limit representation of a differentiation, similar to a point in Euclidean space, but this time this is in a manifold, in the manifold space. So a covariant derivative is also suitable generalization of the classical directional derivative. So all of this is just another terminology to define what a differentiation is of on a manifold. So some other properties, Christoffel symbols, and then the affine connection properties that result from it. And one in particular is its uniqueness at zeros. When you have this uniqueness at zeros, this is a really great one, because once we're going to be using this to perform our geometric optimization, and once we do then we minimize it and find a convergence. So once you find that it is a geodesic, that means that it is a zero, then that means it's a unique, and then you find a solution at that point. So you'll be using this a lot for our affine connection property. So now to define more important definitions. So as I said, you don't define vectors on the manifold, you define them on the tangent space, which is at the tangent point, a tangent at a point of the space at a manifold. Because you have this two space, the tangent space on the Euclidean, there's a Euclidean space and the manifold space and a Riemannian manifold, then you have to perform two types of mappings. So as in vector calculus, you did vector addition. The generalization of that is the exponential mapping. And then you also have, let me just show you this. So this right here is what I said. So for example, what if you had a point at P, and this P on the manifold has this tangent plane, and within this tangent plane you have the tangent space that is tangent at this point. And in order to find this geodesic curve, which is what we want to do on the manifold in order to perform any type of analysis, is we want to find this geodesic curve which minimizes the path between the points within our data set. And because you have these two spaces, you're going to have to define two types of mapping. So the exponential mapping is a mapping from the tangent space into the manifold. So from the tangent space into the manifold. And then the second type of mapping is logarithmic mapping, which is the inverse of the exponential mapping, which is just a mapping from the manifold into the tangent space. So the exponential mapping is the generalization of vector addition, and the logarithmic is a generalization of vector subtraction. And then you perform an exponential mapping when you go from the tangent space into the manifold, and you perform a logarithmic mapping when you go from the manifold to the tangent space. And how these two will be related is when we finally perform a geometric optimization. I'll talk about that in a bit, but for now, since you have all these different mappings are iterated so many times once you perform the optimization. Oftentimes you're going to lose some of the vector magnitude and direction similarities. So in order to map it back to where it is for each iteration, you have to perform parallel transport. So that's just looking at here. For example, when you have A, B, sometimes when you map from A to B, the direction changes. In order for them to be parallel, but hence parallel transport, you have to perform parallel transport at each iteration of the optimization, geometric optimization. So now let's talk about the geometric optimization. So a geometric optimization involves using exponential mapping, as I mentioned, that generalizes the concept of moving straight in the direction of the tangent vector. And it's a natural way to update an iteration given a search direction in the tangent space. So this, in layman's terms, is just trying to perform the mapping from the point in the tangent space back to the manifold in order to find this distance, this geodesic distance, and you do this as many times as you can to minimize the error. So what error are we talking about here? So let's talk about it. So geometric optimization involves approximating this Christoffel symbol. So this is the equation for it. This is really just the numerical aspect of it. But what it is, the result of this geometric optimization is this minimizing geodesics. And so I'll read this. If M is a manifold, a Riemannian manifold, specifically, there exists a curve, this geodesics, with a minimal length between 2 points within the manifold. There's always a monotone parameterization of a geodesic relative to the Riemannian connection, or affine connection. And these are called minimizing geodesics. So the notion here is you have this data set, you have this underlying manifold that you're trying to create, the embedding of the data set from each manifold, for each manifold or points in the manifold, you have to map this to the tangent space via logarithmic mapping, and then you you compute the gradients. From the gradients, you map this back from the tangent space back to the manifold space in order to compute the next point. And this, in essence, what you're trying to do is minimize the geodesics or the line that connects these 2 points. Hence, allows you to really capture and map the manifold structured representation of your data set. So how this is applied. So let's talk about the definitions here. So as we've learned in the past, what is a linear regression? So once you're given a set of points, you can graph a line through it, which allows you to describe its underlying structure and allows you to use its predictive power to be used on future data. So this Y is the independent data, with the dependent this X is the independent data and Y is the dependent data. Once you perform this, you're going to create this line. As you remember, there's the y-intercept and then the slope. In general, the slope is the weight function in data science, and then you also use this bias term for the y-intercept. And you also have this random noise parameter, which we'll use to describe or to randomize the noise to make it more accurate and to describe more data. And so this can only be used in Euclidean space. What if you're in the manifold space? Then this doesn't really apply. You have to use geodesic regression, not linear regression. So this line is generalized into this linear equation. It's an addition, linear vector addition. Is generalized into an exponential function, transcendental function, which kind of confirms, as what we mentioned, that the exponential function or mapping is the generalization of vector addition. And so look at this linear addition from linear regression and exponential transcendental function in geodesic regression. So just to summarize what this geodesic regression gives us, and the mathematical construct of it is, now that you have this, you want to be able to minimize the error. And how you minimize the error is you have this error function defined for this line. And so what you can do to minimize it is to do a gradient descent. So a gradient descent, this is just minimizing the error function. And how you perform a gradient descent is you need to compute the derivatives of your geodesic distance with respect to the points. And This, in essence, computing the gradients involves computing the log maps. So the log maps, when you do the gradient descent, you first compute the log map, which maps the points from the manifold to the tangent space where you compute your gradients, and you minimize the error by computing the gradients back to the you minimize the error. And once it's minimized, you put it back to the manifold space using exponential mapping, and that in essence is geodesic regression. And now let's move on to the embedding. So once you perform an embedding, what you're trying to do is not minimize an error function, but specifically the loss function. So the loss function here, and they're very similar though, is as you can see, this L is loss function involves a logarithm. So kind of similar to what we have here. So as you said, the gradient of the geodesic distance with respect to the points is a log map. So is the loss function. It's a log map of the embeddings. These embeddings are these phi terms. And then I'm not going to explain all of this, but then the embeddings, this sigma term is a sigmoid function, which is used to optimize our function here. Loss function allows us to minimize it. But then, so in essence, what we'll use with the loss function is we're going to be performing this geometric optimization, very similar Riemannian optimization, but instead of the error function of our line from the geodesic regression, in the embeddings, we'll be minimizing the loss function and performing the Riemannian optimization of the loss function. And we do this with a bunch of iterations, and each iteration we're going to be reducing this learning rate. This learning rate is like the step size. That allows us to step towards the optimization. The smaller our steps are, the better our accuracy of our model. So now, with all that definitions behind, let's talk about the one particular example, just to give us a sense of that we're applying and know what a geodesic is. So for a sphere geodesics, let's consider a unit sphere endowed with Riemannian metric obtained by the embedding in an Rn. And it's associated with a Riemannian connection, which is an affine connection of our geodesics. So if you have this is this Riemannian submanifold of the Euclidean space. So we have this projection, right? Projection of the field here, and then this Riemannian connection, applying the affine connection, which is just taking the different, the second derivative of your projection here, is this. And then from all of that, we can find this geodesics positional term xt, and then to verify that this is a geodesic. Remember, geodesics is just the shortest line that has zero acceleration, which means that the affine connection is occur with zero acceleration. So we take the derivative, second derivative of this geodesics, and then if it's zero, then that means it is indeed a geodesics, which it is. And so we also can perform the verification on orthogonal Seifel manifolds. So as Grassmann manifold geodesics, they all become zero. So that means that we can compute a geodesics in each manifold. So with all of that, let's actually talk about implementing geodesic data analysis on a manifold. So before that, let's talk about some of the existing Python modules that's already used out there. And there's a lot. And I'm surprised actually that because this is quite complicated. In essence, the existing Python packages that are already out are PyMaOff, Geoff, and then also have MC-Torch, and then PyCriterion. I've included the websites here if you guys have any interest in checking them out. But the one that I'm most interested in is called Geomstats and Numpy. Numpy, I think everyone has learned Numpy for Python, and that is just using like matrices and vector operations that allows us to really implement what we just talked about with all the geodesic metrics. And so what Geomstats has is it has this geometry and learning modules, and from here you're going to see something familiar. You have a Riemannian metric class that allows you to compute the tangent vectors or inner product of the two tangent vectors, as well as the geodesic distance between 2 points. And then the most important, exponential and logarithmic maps. So it allows you to do the gradient descent. And then you have this manifold class, which allows you to create the embedding, the hyperbolic or spherical embedding, to capture the structure of your data set. So let's actually, instead of talking about it and computing, let's actually implement it. So for our first case study, we have the geodesic regression. So in this geodesic regression, what we will do is we will create a spherical manifold, and we will perform a regression algorithm on past training data with future labels to find the shape of the data set that allows us to predict on tests or future data. So the very first thing that we will do is load up the dependencies. So the ones that we're going to be using for this case study is Numpy and Matplotlib, because we're going to be I believe I didn't actually use Matplotlib here, but I could have plotted it, but mainly Numpy. And then so the second step here is to define the metrics, the geodesic metrics that we just defined: geodesic distance, log maps, exponential map, and parallel transport. And then the third step here is you could generate your own data set. You could have read from any sort of data out there. You could just use pandas for that. So with that, we initialize the number of data points. It's number of 20 data points here, fairly small data set. And then we use some statistics to generate the distribution of the points. And then we also set the labels for our parameters that we'll be comparing. And so from these parameters, we generate the training set as well as the testing set and the labels that we'll compare. So Y will be the labels that will compare our approximation from our regression. So once we have that, the next step here is to implement the geodesic regression by computing the gradients at the parameters P and V, as I mentioned here. And we define how we do this is we have to define the log map, which is utilized in computing the error function. And with this, the gradient descent is performed by iterations of computing the exponential map and parallel transport to minimize the error function. And that's the essence of the implementation of geodesic regression. To explain the exponential functions here are used, and we will be to update the parameters, because the gradients obtained from the log map in order to compute the error function are vectors. And so a gradient is a vector, so points on a manifold cannot apply vector operations. As I mentioned, there's no vectors on manifolds, so that's why we have to do the exponential map by updating the parameters. Also, the parallel transport, as I mentioned, is to help assist in maintaining the location of the parameters that has the same vector magnitude and direction at each iteration. So just to show you what that is, so these are the gradients that we use in the log maps that will map the points from the manifold to the tangent space, and which will perform differential calculus, and which we find the gradients at each of these parameters. From here, we compute the error function, and then this error function, we then use these gradients and minimize this error function by performing the exponential mapping from the tangent space back to the manifold space. And then we increase the number of iterations, and LR here is a learning rate. So learning rate, as I mentioned, the smaller learning rate, the better your accuracy, and the more iterations you have, the better you can capture the underlying features of your data. And so with that, we compute the actual values we compute the approximate versus the actual data values that we already had. And then as you can see, they're quite similar. How so? Let's actually use some performance metrics to compute the error and accuracy rates. So with all of that, using so amount of iterations and small amounts of learning rate, we get an accuracy of almost 97%, and a very low error rate. So error rate is just the inverse of the accuracy. So what you can do is to tune this geometric regression model is to, as I've done, is to increase the number of iterations and lower the learning rates. And this should yield a lower error rate and an increased amount or a higher accurate rate. So just play around with that. Now let's move on to the hyperbolic embedding. So hyperbolic embedding is just performing a clustering algorithm on training data without pass labels to find the probability of distribution or embedding that generated the data. And in general, the implementation of this, we've already talked about it from loss functions as well as the Riemannian optimization. Let's just talk about how we use Python here. So first things first, we load the dependencies. So we have Geomstats mainly. Geomstats has NumPy, so technically all this is just using NumPy. And from there, we start with defining the hyperparameters. So just to speak about this briefly, these hyperparameters can be tuned to optimize the data as we've done with the iterations as well as the learning rate, which is also in here. But this has a few more. So these random numbers or seeds define the pseudo-random numbers. So pretty much it'll give you a random number so that it generates your data in a very accurate manner that's not picked out. So this dimension is the manifold dimension size of your manifold on the embedding. And the epochs here is just another name for iteration. This is how many times we're going to iterate the mappings and the minimizing the geodesics for learning the embedding or the manifold that underlies your data. And the learner is a subset of your iterations. The smaller it is, the better. The number of negative samples in this case is the number of data set that you have on the size of your data set, and then the context size is the size of your data points. Okay, so the next step here is declaring, initializing your data set. Just to explain what these are, these vertices is the information on your data set, and then these edges is the relationship between the data set or the nodes. And then the next step is defining the geodesic metrics. So the gradient squared distance defines the gradient of the square distance based on the manifold representation. And then the log sigmoid, I said this, and the grad log sigmoid, this is just an optimization that will help us minimize our loss function. And our loss function finally computes the errors and gradients using the size of the context and the samples, sizes of your data. And then this loss function we'll use Riemannian optimization of this to really capture the appropriate embedding of our data set. So now the next step here, again, we generate a synthetic data set. You could have easily just used pandas to load in your own data. And then here, just to talk about it, so how I'm performing this data generation is we first initialize the array to hold the embeddings. So the embeddings that we think is the shape of our data on the manifold, and then we compute the random walks. So this array holds embed will have each node with the random points in the manifold. Then to prepare the context nodes for each node, we compute random walks. Random walk is just a stochastic way of walking through our data, so that we're not really picking them out. It's all stochastic. So initialize each step at some length, so some random length, and then use the next nodes from the random walk from defining the next nodes using the random walk from the other nodes. So with that, we use negatively sampled nodes are selected according to what the previously defined probability distribution of your embedding. So with that, with the data set defined, we can perform hyperbolic embedding to conduct the clustering on our data set. And how this is performed is optimizing the loss function numerically over the number of iterations. At each iteration, the gradient of the loss function are computed. Then the nodes are moved along direction pointed by the gradient. Movement of the nodes is performed by following the geodesics in the gradient direction. Using an appropriate size learning rate and smaller learning rate, we can obtain the embedding most appropriate for their data set. So from this implementation, the first loop here is just looping through the number of iterations that will record the value of the loss function at each iteration. So it tracks us if we have the right minimum geodesics of the embedding. The second loop iterates across the path of the random walk. It allows us to properly capture the structure, our data. And then the third loop iterates through the nodes, which allows us to compute the gradients and perform gradient descents to minimize the error function. So this is the implementation of that. First for loop in the epoch, for loop in the random walks, for loop in each of the nodes. And this is the result of that. So for each iteration, you have the loss value, and as you can see, it starts pretty high, 1.71, reduces to 1.28. So it's reducing, which is good, minimizing the loss function. So from here, we display the clustering, and then, as you can see, from this particular data set, we have two clusters that is captured by our clustering algorithm, group 1 and group 2. And then you might be wondering, how can we conduct performance tests on this on unsupervised learning if we don't have any past feature labels? Well, we could perform comparison testing, and where what we already know from the past that actually works. We can use k-means clustering, which is a very well-known type of clustering algorithm, and then kind of find the and kind of overlap them to see if they come up with the same type of clustering. So that's what we'll use. We're going to be using k-means clustering. So this is just that algorithm, and then this is the result, just to show you that it works. So the green and the blue here is the same as what we had with our hyperbolic embedding clustering, and then the stars here are the centroids of the k-means clustering. Since the stars are in the middle, or roughly in the middle of these two clustering, that means that our model is good. So with all of that, these are my references, and I also attached the Python code for your interests, and hope you guys like my presentation. Thank you very much.